So good afternoon, everyone. We're going to get the webinar started here now. It's a little afternoon. First, good afternoon. I want to thank everyone for attending this webinar, Treatability Testing for Remedial Design. I hope all the attendees can get some useful information out of the presentation. This webinar will be approximately an hour. We'll have 50 minutes for the presentation itself, and then maybe about 10 minutes for the presenters to answer some questions. Please use the questions tab on the GoToWebinar control panel to submit your questions, and we'll try to address them at the end of the webinar, depending upon time. If we don't get to all of them, we may answer them via email afterwards. My name is Dennis Keene. I'm a VP here at XDD Environmental. Our presenters are going to be the following. For Mike Marley, who is principal and founder of XDD Environmental. Mike has over 30 years of experience in environmental and civil engineering. Mike is a nationally known expert who focuses on strategies for site closure, including the development and application of innovative remedial technologies for contaminated soils and groundwater. Mike has been at the forefront of developing design and application protocols for soil vapor extraction, sparging, and in-situ chemical oxidation technologies. The other presenter for this afternoon will be Laurel Crawford, who is our Treatability Lab Manager. Laurel has over 15 years of experience in environmental and laboratory projects. She has an extensive background in various environmental remediation technologies and is also the laboratory manager at XDD. His responsibilities include day-to-day operations, treatability testing design, oversight, and data interpretation. So now on to the presentation. So the first question is, why listen to XDD? The real answer is experience. Our staff has been focused on remediation since the early 1980s. As we mentioned in Mike's bio, we've been involved in the early development of most of the major remediation technologies out there, which include soil vapor extraction, air sparging, ISCO, ISCR, in-situ chemical reduction, aerobic and anaerobic bioremediation, thermally enhanced remediation, and vapor intrusion. We've been involved in the design and performance of treatability testing for end users, consultants, and various contractors. We have a wide range of capabilities for in-situ remediation and experience to solve difficult design problems. I'm going to hand off the next section here to Laurel Crawford, who's going to go into our treatability laboratory services, and then we'll get into the main presentation. Thank you. Laurel.
Thank you, Dennis. XDD provides several treatability services, with this slide showing a comprehensive list. We provide the chemical oxidation services listed here. Activated persulfate includes iron and alkaline activated, but we've also tested emerging technologies such as potassium persulfate, which has a low solubility, with the advantage of establishing a slow release source for persulfate, which could be appropriate for a barrier application. We've tested the chemical reduction technologies. We've also conducted several microcosm studies for bioremediation, both aerobic and anaerobic. We've also conducted a sequential study where we looked at anaerobic treatment of tri- and dichlorobenzenes to degrade di- and trichlorobenzenes to chlorobenzenes, followed by anaerobic treatment of chlorobenzenes. We've conducted in situ stabilization and solidification bench studies. We've also conducted thermal enhancement studies, which we'll show a case study for in a little bit. We've recently been getting into surfactant enhanced products recovery, working with EcoVac services. And I'd like to also mention that we're approved to receive and test international soils, which we've conducted about 3 bench studies for thus far. But most importantly, we can customize any testing to meet the client's needs, from simple design parameters such as SOD to more involved testing to look at treatability of site contaminants. We offer several in-house treatability services, including in-house analytical capabilities. We offer this as more of a screening technologies, we look at dissolved gases by gas chromatograph, also volatile organic compounds by gas chromatograph. We can look at various anions and organic acids, formate, lactate, acetate, propionate, as well as butyrate. And we can also look at molecular hydrogen using a gas reduction analysis method. But again, these are more of a screening analysis. XDD is not a certified analytical laboratory, so depending on the project needs, we will send out samples to a certified laboratory for analysis. So why conduct treatability studies? It's important to have certainty of success for a full-scale field application. You want to have the appropriate remedial design before going into the field and spending tens to hundreds of thousands of dollars on a remedial event, whereas treatability studies typically cost less than a tenth of a field application. So if you don't test it at the bench scale, you can save a lot of money in the long run by determining the appropriate design parameters. XDD often bench tests several technologies to determine this. Through bench testing, we determine potential failure mechanisms. For example, for oxidant selection, if you have a high base buffering demand, you can potentially increase the cost. For example, an alkaline activated persulfate application by having to use a lot of sodium hydroxide for full-scale application of that. So you want to determine the right dosing requirements to meet the contaminant demand as well as non-target demand. So soil oxidant demand is an important factor, but also bench testing can help you determine adverse reactions between the oxidant and soil and groundwater from your site, such as gas and heat formation that can often form during hydrogen peroxide reactions. It's also important to determine field design parameters for bioremediation. So whether you have the appropriate bacteria present or not, if you have the appropriate bacteria, you need to amend with nutrients. If you don't have the bacteria present, you need to bio-augment potentially. It's also important to determine if you have the correct geochemistry, such as pH and ORP, as bacteria thrive best at around a neutral pH range between 6.5 and 7.5. There can also be toxins present, such as high salinity, that can be an adverse reaction for bioremediation. Bench testing can also help determine if there are secondary effects, such as metals mobilization and byproducts. So determining how much reagents to apply in the field can result in cost savings because overdosing is less likely, but also underdosing is avoided, which can often result in apparent failure and more mobilization events. So our first case study is an example of where a treatability study helped to select the right technology. Initially, catalyzed hydrogen peroxide, CHP, was selected by the Army Corps of Engineers for treatment of chlorobenzenes in weathered bedrock and soil. The Army Corps approached XDD because they wanted to apply CHP in the field. XDD noticed, however, that a bench study conducted by others was performed on thermally treated soils. So we were concerned that these soils wouldn't be representative. So we convinced the Army Corps to allow us to bench test CHP, but also to persulfate to verify the feasibility of applying these or whichever oxidant worked better in the field. CHP ended up working very well in the bench testing. However, it had a very short half-life. Activated persulfate worked well and was a lot more stable than CHP. The Army Corps still required us to conduct side-by-side pilot tests to prove the bench results. And the pilot test confirmed CHP failure, so because of the short half-life, there was instability and minimal effective radius of influence. And it turned out persulfate was successful due to enhanced stability and contact with the soils and groundwaters away from the injection points. As it turned out, the thermally treated soils were not representative of the in situ soils. Ultimately, persulfate was applied successfully at the full scale, saving hundreds of thousands of dollars on a failed application. Another case study was a Navy site, and this example was another treatability study that helped us select the right technology. We evaluated several oxidation and reduction technologies for the treatment of carbon tetrachloride. Reduction technologies included ZVI and coated ZVI, but these reduction technologies were eliminated due to failure mechanisms. Specifically, they formed byproducts that were recalcitrant to further reduction, for example, chloroform. We ended up selecting alkaline activated persulfate, and through the bench testing determined the right approach and design and dosage for the field. It was applied successfully at the pilot and full scale, ultimately saving time and cost by implementing a technology that met the project goals. And at this point, I'm going to turn it over to Mike Marley.
Okay, good afternoon. What Laurel's been talking about is basically what treatability studies we are capable of doing, but also basically some of the major benefits with that. And I think one of the things that's happened in the industry that you probably have recognized or seen out there is there's a lot of, and there's always been a lot of price pressures, but I'm seeing more and more price pressures to basically cut corners or go with the cheapest that's possible. With that, basically, you start to see a lot more failures happening out there. And basically, the failures are because of what Laurel said earlier. It's really about certainty. If you do the right thing, if you basically evaluate what is necessary for you to have a high level of success and you apply that, you will have a high level of success. But there's a lot of pressures to push the other direction, which is basically, well, what can we get away with? And the straight out practice basically tends to be more rule of thumb, not necessarily good remedial design approaches. It's got lower costs associated with it in most cases, but you're dealing with a lower certainty. It doesn't mean it won't work, it just means the certainty of it working is much less. And in that context, we're going to talk about a few case studies with regard to the state of the practice, state of the art. Again, just an illustration on dosing of the reagents, whether it's a biological process, whether it's a chemical process. Typically, that's one of the big failure mechanisms that you see in the industry. And typically, when you go through the design process, you do your treatability studies, and you basically find out what you really need, as illustrated in the cartoon. But this is a lot of times what you get, and this is basically the source of a lot of the failures, is basically in an attempt to be more cost effective, and basically you're underdosing with what is required, and as a result, you achieve a failure. The message basically is the state of the practice, which is happening out there a lot more than you would think, is basically skipping a lot of these remedial design steps that we may have done more in the past, again, because of pricing pressures, doing the proper tactical evaluations and treatability studies. We do them, others do them, but the key is they're a very important part of the design process for many technologies. Not all technologies, but for many technologies, they're very applicable to basically, again, as Laurel pointed out, to eliminate any failures, going with the wrong technology for the particular soil conditions and geochemistries or contaminants. Make sure that you're in the right range for what dosing is going to be required, and identify any potential interferences or failure mechanisms. You know, field scale pilot testing, again, for not all technologies, but for a lot of technologies, is another good step in that process. We're going to focus again on the treatability aspects. So one of the common state-of-the practices that has developed in terms of reducing the amount of remedial design that our people or engineering companies are putting into these are the development of the product vendors with the spreadsheets that they have for remedial design. I have no issue basically with these products, or even, you know, the vendor companies. They're producing good products that have ability to add oxygen for the like of an oxygen releasing compound, add an oxidant to the system in a more usable form to the subsurface. The issue that really comes about in the state of the practice is, as a consulting firm or as an end user, basically data has been collected on your site, and the site information is then provided to the product vendor, and they're doing the job that they are appropriately doing, which is they're inputting that information into a spreadsheet to determine what the dosing requirements are. The issue is, again, not the vendor, not the product. It's the remedial design element. There's always parameters that a typical RI does not, or characterization, site characterization does not measure. And those can be detailed geochemistry for like chemical oxidation. It was mentioned about CHP. CHP's failure mechanism is, as Laurel pointed out in the example, the potential for a very short half-life, even in the presence of a chelate that would tie up some of the mineral surfaces that are responsible for that rapid dissociation. You're not going to measure, nobody's going to measure what the mineral surfaces are in the subsurface because it's not cost effective to do so. So a treatability study is a cost effective way to find out if that's an issue. Another typical issue that I come across is people got a petroleum site, for example, and the regulators are most concerned about BTEX and PAHs. And basically that information is provided to the product vendors and they'll determine their dosing. And because of the uncertainty or unknowns, there's typically a factor of safety put in, but it's a guess. It's a guess as to what might be the added demand beyond the target contaminants. And being a guess, it brings uncertainty into this. By actually measuring some of these sensitive parameters, for example, in an oxidation process, for measuring the non-target demand of the oxidant, it's mentioned here as an SOD or a TOD. The difference being SOD is supposed to represent the non-contaminated soils. TODs are supposed to represent the total demand with the contaminants associated. They're typically not measured in the characterization phase. And without that number, again, you're guessing at what that actual demand or what that dosing should be. Similarly, for a biological process, if you're going with an aerobic biological process, you need to know what's the non-target demand for oxygen. You've got natural organics, reduced minerals, you've got basically a lot of things that are making up a demand for oxygen beyond your target contaminants. And without that, again, you're introducing uncertainty into it. You can also have interferences, scavengers for the oxidants or for the oxygen in the subsurface that, again, aren't typically part of your characterization phase and therefore basically are an unknown. That, again, you've got two choices. You can guess on a factor of safety, or you can measure what it is and have a higher certainty. And there's other very site-specific parameters. The case study, next is a case study basically that I want to talk about that illustrates that example. This is a Superfund site basically where we were contracted by the EPA contractor for a Superfund site in South Carolina, which had multiple source areas, chlorinated solvents, petroleum. They were particularly interested in the petroleum plume, and they wanted to add oxygen release compounds to that. So we took the characterization data that was available. We provided that to 3 of the oxygen releasing product vendors. And again, the products are fine, the vendors are fine, it's the remedial design I want to focus on. So given the information that they were given, we asked them we're going to run a treatability study, we're going to have this much soil, this much groundwater from the site, and we're going to run this, and we want to know how much of your product is necessary to do a 90% reduction in the petroleum contaminant in this, so that we can do a comparison between the available products to recommend for this site. When we provided that site-specific information, we essentially got back 3 different answers. We also had a control. So we got 3 different answers basically as to how much of the product was necessary to achieve the 90% reduction for the same characterization information provided. And part of that is, again, because there's a factor of safety that's added in there that's going to be variable depending on, competition between the vendors, and also basically what their experience would suggest it might be a reasonable factor of safety or a good guess. But to eliminate sort of one of the amount of product, the dosing that they suggest, we chose the maximum dosing that any of those 3 provided us, and we applied that to all 3 treatment studies. Some of the vendors did actually recommend treatability testing to validate the dosage, which is a good thing to do, but the industry for the most part ignores that and basically typically goes with these dosings. That's what I've seen personally. The results of that analysis are illustrated in this diagram. Where basically, don't forget again, 1 dose was supposed to get a 90% reduction in the contaminant concentration based on the characterization data and whatever factor of safety was implemented. You can see basically that for dose 1, which is the full dose expected to achieve 90%, the highest recorded reduction in the petroleum hydrocarbon mass in the reactor was 18%. So again, whatever factor of safety was incorporated into those estimates for those loadings was inadequate because of non-target demands that are not typically available to you in the characterization phase. We had enough in the budget for the treatability study to do a 2nd and a 3rd full dose of oxygen releasing compound, again, single dose meaning to get a 90% reduction, and you can see that 57% reduction was the highest we got after 3 doses. So again, if you're in the field, you're talking to your client, you're basically talking about, hey, 1 dose of this is supposed to be adequate, 3 doses later, triple the price, and you're not in a good situation. A treatability study would have basically determined the correct dosing, would have eliminated that guesswork, and basically give you a much higher success probability. Turn it back over to Laurel before we get. I'll come back and talk a little more about some other case studies where the treatability study has been beneficial and ended up in a high success for the remedial system. But Laurel's going to talk a little more about how the treatability studies are run.
Yeah, a typical treatability test setup is conducted in a series of batch reactors, like pictured below. These are probably, our typical SOD test reactors. If we have a treatability test where we're looking at volatile organic compounds, we would try to have little to no headspace in BOA vials, or if we're looking at SVOCs, something that the lab would require greater volume for, they might be larger batch reactors. But we've also conducted column studies, which you'll see an example picture of in a case study later on. Our controls are carried through the same procedures and throughout the duration of the test as the reactors with oxidants, or in the case of bio, whether we have amendments or bio-augmentation reactors. And the controls for bioremediation tests consist of typically a killed control by lowering to below a pH of 2. ISCO controls consist of just a site media with no oxidants. We usually conduct our tests in duplicate or triplicate for purposes of analytical precision. Soil often has a lot of heterogeneities, so it's particularly important for those tests that involve soil. And we do typically try to involve soil in studies. There are cases where we only had groundwater available and the client couldn't get us soil, but the soil is important to incorporate, so you get the non-target demand and the geochemical interactions. The test design groundwater-soil ratio is important to approximate your field conditions. So low pore volume of reagents added to approximate what you're applying in the field. We have seen bench tests performed with a high groundwater-soil ratio, but that is really representing multiple applications. As we mentioned previously, we test multiple technologies, screening tests for emerging contaminants such as 1,4-dioxane and PFCs. We'll test various oxidants to determine potential failure mechanisms, like previously mentioned CHP stability with gas and heat that can often be produced. And most importantly, like mentioned previously, we'll customize our bench tests to the client's specific needs. And non-target demand requirements are important to determine your test range and oxygen concentrations likely for a field application. And in terms of the duration, media requirements, and cost, a test duration for ISCO can be anywhere from a couple days for like a CHP stability test to 8 weeks if we're doing like a persulfate or permanganate soil oxidant demand test, or longer if we're adding on a treatability test where we need to send samples to a laboratory and wait for analytical results. Bio can last anywhere from 2 to 6 months, aerobic tests being on the shorter end of the range, and anaerobic being 6 months or longer. Media requirements can be anywhere from 2 to 30 pounds of soil, groundwater 1 to 20 liters, again, depending on the scope of the test. And it's important to get the media from your area of interest. For example, in the earlier case study, we found out that the soil samples were collected from an accessible area, but was nowhere near the source area. So that example, the thermally treated soils were just not representative of the site area that we needed to treat. And waste handling is in accordance with a small quantity generator status, and we handle in accordance with a licensed waste facility. Costs of bench tests, again, can vary anywhere from a couple thousand to 50,000 or greater, depending on the scope and number of samples. And at this point, I'll turn it back over to Mike.
Okay, we have a few case studies basically, and again, the case studies are focused on the treatability aspects and the benefit. This particular one was an interesting one where 1,4-dioxane basically was in landfill leachate, and the system that was installed and operated for many years before 1,4-dioxane became concerned was a typical pump and treat system with filtration and activated carbon. As a result of the regulations and the interest in 1,4-dioxane, sampling was done, and as expected, the 1,4-dioxane was passing through that system and being discharged. So the interest was, well, what could be done to add on to the existing system and basically to treat the 1,4-dioxane? So 1,4-dioxane is basically easily dealt with oxidation processes. It can also be dealt with biological processes, typically aerobic co-metabolic processes, but in this particular one, it was going to be easier to attach an advanced oxidation process using ozone and peroxide. It's not the only advanced oxidation process applicable, but this was the one of interest and most available. The objective, obviously, was to knock the 1,4-dioxane down to the regulatory standard, which was about 0.3, 0.4 ppb. Originally, it was 3, but basically over the time frame of the evaluation, it was dropped down. The complication of this particular site, and for you to be aware with when you're doing the advanced oxidation processes, this particular site actually had a pretty high bromide concentration. And for those that are familiar, one of the issues with ozone in contact with bromide is the formation of bromate. And bromate, therefore, can be formed, and there is a regulatory standard of about 10 parts per billion for bromate. So the difficulty with this particular site and the evaluation is balancing the amount of ozone to add to the peroxide to be effectively oxidizing the 1,4-dioxane. At the same time, trying to maintain an ozone level that basically was such that you weren't going to form bromate above regulatory standards. So the data basically, and again, as I mentioned, the reaction is the hydroxide and ozone forming the hydroxyl free radical, which is very effective. But again, bromate is the one to basically be concerned about. This is just an example of during the treatability study, and it shows, it's a busy slide, but really what we're looking at is we were doing a fixed peroxide ozone molar ratio of 1. And we're looking at different doses of ozone for, and obviously peroxide under those conditions for a high concentration of 240 parts per billion of 1,4-dioxane. And you can see basically that we were able to drop down the 1,4-dioxane fairly readily with this 1-to-1 molar ratio. But as you can see, as we added more ozone, more peroxide, we were more effective on the 1,4-dioxane. But you can see on the right side columns, for the same conditions, you're starting to form more and more bromate. So the bromate is exceeding the regulatory criteria. And this showed the whole balancing act that had to happen with basically, we had to change the molar ratios of hydrogen peroxide to ozone to get something more meaningful and more able to do the balanced destruction of that system. Again, it's something that without the treatability evaluation, you wouldn't be able to know that that was going to be a problem, and you weren't going to be able to come up with a solution for it. That's just one example.
So the next case study here, and I'll present this, is thermal enhancement. The question is thermal enhancement beneficial, cost effective? Right. So site history, this is a site with one of our partner consultants. Manufacturing operations were from 1910 to about 1997. RIFS was done in the middle of the 90s. 2004, essentially all the operations ceased and the buildings were essentially demolished and removed. There's low permeability layers that are varied in thickness and depths across the site. The site contains both VOCs and SVOCs, and generally there's an aggressive remediation schedule at this particular site. So this site was designed to go thermal, essentially based upon negotiations with the regulatory agencies. We were approached by the client in order to conduct a treatability test to answer some basic questions associated with the actual design part of the process. So the question is, what temperature is needed for the site using thermal, right? What are you going to get for a particular degree levels associated with the heating of the soil? So we designed some flow-through column experiments. We did 3 soils for A, B, C, and we did 3 temperatures, 35 degrees Celsius, 50 degrees Celsius, and 70 degrees Celsius. One of the big questions we want to ask at the site with the raised temperature, what extent or what magnitude does bioventing assist the site remediation here? So we had the flow-through column experiments. We transitioned several columns to a bioventing phase, and then measured the oxygen utilization with time for those columns. And then we added nutrients about half the conditions to determine if they were going to be needed for a bioventing system to work most effectively. And here's a quick diagram of the column experiments for areas A, B, and C. We had a water bubbler in there to make sure to keep the soils moist like they would be in natural conditions, and basically to allow the microbial population someplace to exist in. And the results are located on the right. So What we have here is utilization rate of oxygen on the left, and elapsed time in days on the x-axis here. And we can see for the vast majority of these locations, we saw a decrease in the oxygen utilization time, indicating that the system was using oxygen, and the biological microorganisms were using oxygen in order to degrade any organics in the soils here. So, some of our primary treatability observations for this particular site, we had higher impacted soils, were very tight soils and silts. So we ended up doing some additional site permeability testing and using some 3D modeling for the SB design, something that may not have been noticed necessarily without the bench testing. The majority of the treatment actually occurred during the bioventing phase. So there was some treatment of the COCs, both the VOCs and SVOCs, during the thermal SB component, but based upon the oxygen utilization in those columns, the biological population accounted for the vast majority, essentially, of the COC reductions, essentially. The other result was nutrient addition had very little additional benefit. We didn't see that was necessary, so there was some cost savings associated with not doing that in the field. And then, increased temperature did accelerate contaminant reduction some, not necessarily greater than, 50 degrees and 70 degree C column. So the 35 degree C column was essentially considered the most efficient with respect to both SV removal and also the biological transformations. So this system has been operating for a little over a year now. It's been about 8 months of operation for massive VOCs and SVOCs decreased 58% and 73% respectively. If you look at the table, baseline was done in 2007, and then these are late fall 2017 samples as far as the efficiency of the system and its effectiveness. If you look at 2007, we have a total COC amount of about 41,000 pounds. In 2017, it reduced to about 17,000 pounds for a total percent reduction of approximately 60%. I think the takeaway here is, and it's something that would not have been realized had the bench testing and column studies not been completed, is that 86% of the mass reduction occurred via biodegradation. And this was basically estimated by just looking at the oxygen utilization associated with the operational parameters of the system. And then on top of that, we knew what the estimated SB removal mass was for the system, and we were able to look at the difference on the soils to figure out what basically had been removed via the biological processes. So after about 12 months of operation, evaluation of site closure is ongoing. Just recently, regulatory agency had approved essentially 90% of the system to be shut down. So essentially, they're going to be concentrating on two kind of hotter spots that are remaining over the next several months. So the project's been relatively successful up to date.
This particular case study, again, was a system that basically was downgraded as a chlorinated solvent site in fractured bedrock with a pump and treat containment system. It's up in Maine. And for that particular system, the pump and treat had been operating for a long time, and they wanted to see, can we do anything to knock that down? So the treatability study there was basically looking at, because it was in a fractured system, the biological was considered to be a more appropriate approach. It was more forgiving, if you would, for the presence of the contaminant and the bleeding of those contaminants than possibly an ISCO application. So the treatability study that was done was to determine what's missing from the recipe for the biological anaerobic process to occur. From the treatability study, which was used in the site-specific groundwater and soils or bedrock, obviously they had done a permanganate application a few years previously on the bedrock, and basically they killed off a lot of the food, a lot of the nutrients, a lot of the bacteria as a result of that, which was fine. They had some decent reductions, but again, not able to shut the system down. So the treatability study confirmed there was really not much in the way of food left. There was very limited nutrients. None of the dihalocoides genus necessary to basically do the full reduction of the chlorinated solvents were present, and the pH actually was all over the place, and basically definitely not in the ideal range. Again, it was fractured rock. They were concerned with metals mobilization. The treatability study was able to demonstrate that that was not going to be an issue through the addition of the when the electron donor, nutrients, and appropriate bacteria were added in the bench. We looked for the metals mobilization, and it wasn't an issue within that site. The question that came about was, well, can you tell us how many applications it's going to take? Well, the answer is always, well, can you tell us how much is down there and where it is? And what was said was, hey, if you do the pallet test application in this area, the data that you get from that is able to be diagnosed to basically tell us a lot more about whether it's going to be 2 applications or 20 applications. In this particular case, the pallet, which was really a full-scale application, using push-pull, pull-push, where you pull out the impacted groundwater from that bedrock area, you augment it with the reagents necessary based on the treatability study and add it back to the system. 2 applications were performed of that over about a 12-month period. The first application did show that this was not a large enough mass that it's going to require multiple applications beyond 2 or 3. After the second application, the concentrations did drop sufficiently and stayed at that level post-application, such that the pump and treat system could be shut down. Again, the treatability study was a very important part of diagnosing what was wrong and coming up with a solution. This one, again, focused on treatability study. This is a downtown Manhattan 32-story residential building that was under construction when the New York DC basically said, well, you have a petroleum problem underneath this site. So sort of an emergency, hey, what can we do? We have to get rid of this in short term. We're going to be constructing over this site. It's a one-shot deal, needs to be done quickly. What can be done? Well, to do it right and with a one-shot deal, again, the treatability study was for chemical oxidation, which was the most applicable to meet all the demands, technical and non-technical. And so we looked at multiple oxidants. We looked at the demand for the oxidants to come up with the right dosing. Alkaline activated persulfate jumped out as the best, and the oxidant loading was determined from the treatability study. It was a very tight schedule, as I mentioned before, with 2 weeks to basically get in and out and apply the oxidant to the area of concern, which is actually the staging area for all the materials that were being moved up to the upper floors. There was about 400 construction workers there at the time. Bottom line is, as a result of the treatability study pointing towards the right oxidant in the right time frame, 6 days of chemical injection to meet that loading demand into the subsurface. And you can see from the results projected in the bottom right there with the soils concentration very similar for groundwater, that there was a dramatic decrease in the 99% range, greater than 90%, definitely greater than 99% in the soils. And the concentrations in the groundwater dropped below the regulatory criteria that was for that particular area, which it wasn't MCLs because it's Manhattan. There's a sort of shadow concentration, but it's pretty low, but it's still above MCLs. But it dropped down to below that level, and a couple of years of monitoring post showed it continued to decline, and it was closed by the New York DC. Again, the treatability study was key to identifying that and come up with a cost-effective approach. The last case study basically is, we've mentioned a lot about in situ processes. This is an ex situ process. The first one was with the 1,4-dioxane. This one actually was an interesting one. It's a site that had chlorinated solvents. It also had some petroleum compounds, and it also had dioxin, not 1,4-dioxane, but dioxin. And the approach to take care of that was activated carbon. But because of all the other contaminants in the process, basically there'll be an air stripper to remove some of the volatile components that were also incorporated in this. But from an operational perspective, there was very high iron and also very high dissolved organic carbon and CO2 chemical oxidant demand. So because of those, there was anticipated and there was seen a lot of potential operational issues with fouling. So there was multiple source areas as well. So some of the simple air stripping was enough to knock out some of the iron or precipitate the iron that could be then flocculated and coagulated out and settled out and then as a sludge. But one of the areas in particular, the geochemistry was such that there was also some natural sequential reagents in the system, which were basically not allowing the iron to come out of solution under a simple oxidative process. So that's what required the treatability study was looking at, well, what can be done to basically, for that particular source area. And what we found was a simple pH adjustment up to about 9 was able to break up the sequencer reagents such that the iron would come out of solution or precipitate and be able to be removed from the system. The organic carbon, the TOC moved through that process fairly readily and was not significantly reduced. So one of the other issues was with the GSC, which was being used, the activated carbon, which was used to remove the dioxin. Basically, there was a real concern with the dissolved organic carbon and basically fouling that up or making the demand for that carbon very high. So that in that particular process, the treatability study was able to identify a surface-modified zeolite that is pretty selective towards the organic carbon, and it was able to use to essentially pre-treat for the GSC and remove a lot of the TOC, such that the demand on the activated carbon was significantly reduced and more pronounced for the dioxin removal, which it was. And as per the last bullet here, there was those pre-treatment steps was a significant cost savings to the client to operate that system. I think that basically covers, some of the takeaway message again is basically mainly associated with the fact that to do adequate design and have a high certainty of success, treatability studies are an important aspect of that design. Do you have to do them all the time for every technology? No, but they can be very beneficial, very confidence building, very more accurate on what the costing is for you to do and the right technology for you to use. And they're very effective design tool as part of the design process, which the industry is tending away from, which I think is why we're seeing a lot more failures.
So now that we're done with the presentation component of it, we have 2 or 3 questions here that were asked in the question section of the webinar. We have one question, Mike or Laurel. Talk about the rate of failure due to improper conceptual model versus improper technology selection. What are your
That's a good question. Basically, regardless of what you're going to do, you need a good conceptual model of where your contaminant is and how it's distributed and what its architecture is. Because if you could have 10,000 pounds of contaminant, but if it's sitting as a pool of liquid at the on the top of an aquitard versus it's distributed throughout a 20-foot thickness as a residual, that makes a huge difference to the selection of your remedial technology. At the very start, when Dennis was going through this, we showed a pie chart. We showed 97% success in the projects that we have worked in. The conceptual model actually was one of the 3% failures. A lot of times, we're provided data on these sites from characterization or conceptual model development. And for one particular site, which is New Jersey coal tar site, the information that was provided basically said that the maximum concentration detected in the area for treatment with chemical oxidation is 1,500 milligrams per kilogram. And so we've done the treatability testing. We determined basically that the particular oxidant for that particular site that was going to be the most effective for that level of impacts. And we determined the dosing from the treatability study. So we went to the site. It was underneath the building. They did not want to knock the building down. It was residential standards for soils based on the location where it was and the future use. And we applied the application of the ISCO. The post-sampling basically showed that we accomplished a 1,700 milligrams per kilogram reduction, so right in line with what the target was from the characterization data. And the only thing remaining was 2 unidentified lenses of coal tar that were full of coal tar. They were small lenses, they were a couple of inches in thickness, but they hadn't been identified during the characterization phase and the conceptual model development. And basically, as a result of that, it was not going to be cost effective relative to alternatives to apply more oxidant to try and knock those two lenses out from the system. So, you know, in one way, the oxidant did what it was supposed to do. In another way, the goals weren't accomplished. So basically, this is, to your point of conceptual model, very important to understand where the contaminant is, in what condition it is, what is the architecture. Again, if we go out and we treat a quarter of the pie and there's 3/4 left that's still impacted, you're not going to have a success. So yes, very important.
Next question is, what are good site-specific parameters to be looking for testing during a treatability study for in-situ chemical reduction?
Again, a good question that basically, there's a wide range of answers for that. Depends really what you're trying to treat. You're trying to treat a metal, you're trying to treat a chlorinated solvent. But let's take the example of a chlorinated solvent. And you're doing a reducing agent. And again, a reducing agent like ZVI. Probably the number one issue with the ZVI and for the reductive processes, you don't always get a pathway for reduction using ZVI that basically goes full to the end product or the non-toxic end product. So you want to, the treatability study is beneficial basically to be able to demonstrate that you are indeed going to be able to get down. For example, the case study that we said with for the Navy, which was carbon tetrachloride. We used oxidative and reductive technologies for that, and the reductive technologies had a lot of problems. They'd done well to reduce the carbon tetrachloride, but it was a big stall at chloroform. And given the site-specific conditions of groundwater velocities, etc., it was going to be difficult to design a reductive process for that. If you're looking at metals, upgrading geochemistry is very important because the whole idea is to reduce the metals to stabilize them, but depending on what the upgrading geochemistry is, these are reversible reactions, and basically that's very important. So if you've got a low pH coming into your system, for example, at Borden Aquifer back many years ago, when they were looking at in situ chemical oxidation treatment of TCE, they basically were applying permanganate, and the permanganate done a great job of removing a lot of the mass of TCE, but also it formed the manganese dioxide rind, and what they've seen was a dramatic reduction in mass flux of the TCE down gradient as a result of both the destruction but also the formation of these manganese dioxide rind. So they assumed, hey, this is great, and it is a biogeochemical stabilization, is what they coined that for doing that type of thing. The trouble was that the upgrading geochemistry was such that the manganese dioxide was caused to dissolve over long term, so it redissolved, and what happened there is they went from a very high mass flux of TC to a very low mass flux of TC after the treatment to a building level of TCE in mass flux over a decade as a result of the manganese dioxide being dissolved by the upgrading geochemistry. So again, if you have a site-specific question with site-specific contaminants and stuff, we could give you a more specific answer. But that's an example of things that need to be considered basically for reduction technologies.
And I think we have time for one more question. The question is, going from lab treatability test to kind of full-scale remediation of the site, for that scale-up, what are the most important factors to be considered when using these, lab scale results to predict the kind of full-scale application? I suspect one of the things we're going to discuss here is having a lab that's doing the work that actually does the in-situ remediation in the field so they can understand exactly how to do that.
Yeah, again, like the last ones, there's multiple answers to that particular one. Laurel mentioned one thing that I've seen a ton of times, and that is some labs, basically, if they're doing a treatability study, will have a fairly high water to soil ratio, And basically, so they might have a 20-to-1 ratio. So they've got, you know, when you look at pore volumes, which is what Dennis is referring to, when you're looking to go and apply this in the field, and you're going to apply, you know, a pore volume or a couple of pore volumes of, say, chemical oxygen as an example, to basically treat a contaminated soil. If you do a 20-to-1 ratio of groundwater to soil, what you're representing in the field as a scale-up is you're presenting the soil with the equivalent of 20 pore volumes, 20 full pore volumes. Very difficult to get a full pore volume injected into a site. It's more typical to get 50–70% maximum. There's a paper that the EPA just published by Scott Hewling that came out last year, where they looked at a lot of these sites and where people were actually applying 5 or 10% pore volume and getting a high failure rate. There's two reasons for that. One is basically contact, but the other reason is basically just if a treatability study was done with 20-to-1 ratio and it was deemed successful, you've got to consider that basically that was successful partly because you've done 20 pore volumes, so the equivalent of 20 applications of one single pore volume. So that's an important aspect of scale-up. We do our tests basically using 1 to 2 pore volume equivalent soil to groundwater. That's given us a more realistic estimation. The other big thing, obviously, is and Laurel mentioned it, we had another site in Florida where we done a chemical oxidation treatability study for. They didn't give us a lot of site information, and they called a couple of months later and said, well, it didn't work. So I asked them some more questions, only to find out that the soil sample they provided us was basically from the entranceway to the industrial facility because it was handy to get that soil sample, and it wasn't representative of the treatment zone, which actually was not only a chlorinated solvent site, but also was discharged to a septic system. So we had a lot more demand for the oxidant than represented by the soil that was provided initially. And one of the giveaways was they said from the field that they were getting a yellowish tone to the water, which is typical of what you would see with high organic matter and a chemical oxidant. And so that sort of relayed what the problem was. We helped them fix that, and the problem was treated. But so when you want to scale up, you want to make sure that the soils that you're testing are represented. And if you have multiple soils, so if you have an impact in a tight, silty material, but you've got equal impacts in a more permeable material or a clay, you need to treat all of those soils to be able to scale up to what yours. We've had a very successful scale up in a lot of the projects that we have been involved with, either in the treatability phase or in both treatability and full-scale application. And those are the two of the major elements, is making sure you're getting the right dosing by testing the right level of impacts, the right soil distribution, and again, making sure that you're testing the right number of pore volumes. One case study recently that we didn't have in here is, but basically I looked at a treatability study by others for peroxide for a TCE site. And what I found basically was they didn't look at the stability of it worked fine in the lab with regard to reductions in TCE, but when you dug into it, what happened was two things. One is that the half-life of the CHP was basically on the order of a couple of hours. You need a half-life on the order of 18 to 20 hours to distribute it in the subsurface. The other thing that they had one sample for was there was a lot of gas produced because of the rapid dissociation. There was one sample that they took of the concentration of TC in the vapor phase that developed the oxygen that basically developed from the dissociation of the CHP. The concentrations in that gas phase combined with the amount of gas that was being developed was sufficient to account for all the TC loss from the system. So essentially it was stripped out of that system as a result of oxygen generation. And in the field application, we were called in after the field application at field. The field application basically was tremendous amount of surfacing and total failure of TC remediation because a lot of oxygen was distributed. It all came up around the wells. There was some stripping, but very minor compared to the total surface area that was to be treated, and ended up as sort of like a ineffective system. Again, could have been addressed by a proper treatability, looking at scaling up. As Dennis pointed out, if you're out there doing lab tests and you're not doing field implementation, you're not necessarily thinking of these aspects, and you could be given a false positive in the treatability results.
One last question is for sulfate treatability studies. Have we ever examined the role of naturally occurring iron for activation purposes?
I think basically when we're, Laurel mentioned earlier that we're basically, we also do unactivated persulfate, is part of the testing procedure many times. And basically, yes, natural iron basically can be more than sufficient to do a iron activated persulfate application. In some cases, we don't need to put an iron at all to have an iron activated persulfate happen in the field. And basically, you can tell that when you do an unactivated persulfate application, you can tell by what occurs in that lab that you're basically having a lot of natural activation of the iron. Iron activation will dramatically go down fast to a low pH in the range of about pH of 2 in a typical system, and you can see this effect.
Okay, that's all our questions, and that's all our time, so we've used it perfectly, it appears. I'd like to thank everyone again for attending the webinar. We'll be shooting out an email that contains a link to a video of the presentation and also the slides, and if there are any additional questions, at the end of the presentation here, we have both Mike and Laurel's email address and our phone numbers, so if you'd like to call us any additional questions, please feel free. That ends the webinar, and thank you very much. Appreciate it.